Okay, so now let's talk some more about sequential circuits and look at analyzing a particular sequential network. Okay, so given a sequential circuit, I have two D flip-flops, one that I've labeled A and one that I've labeled B, and then some combinational logic to generate the output Z, as well as taking the state of my flip-flops and also the input X to generate the inputs to these D flip-flops. So the first thing I'll do is I'll go ahead and write out the equations for the inputs to each of these flip-flops. So for example, DA looks like this, and DB looks something like this. Okay, and then for sequential circuits, there's an important way that we can model their behavior, and that's called a next state table, which has the current state and the input. And then we can list out our flip-flop inputs to then figure out the next state of my sequential circuit, as well as the output. And the next state we usually label with whatever the variable we're using, so Q or A in this case, and we'll say plus, so A plus for the next state and B plus. Okay, so our flip-flop inputs, we've already written the Boolean expressions for, so we know that DA is a 1 when A is 1 and X is 0, or when B is 0 and X is 1. And for DB, we have a 1 when X is 0 and B is 1, or when X and A are both 1. Now for D flip-flops, it's easy to determine what the next state is based on the inputs because D, and you can think of D standing for data, the data flip-flop, whatever the D input is, that's what my next state is going to be on the next clock edge. So I have something like this. And my output is just when X is 1, A is 0, and B is 1. So a next state table is an important way that we can model or describe the behavior of sequential circuit. In this case, where we can analyze and figure out what this sequential circuit is doing. Another important way that we can model sequential circuit is with a state diagram. So with two flip-flops, there are 4 possible combinations or 4 states that my circuit can be in. And then with a state diagram, I can label those states differently with letters, a specific name, or in this case, I'll just use the bits. So I have 4 states, 0, 0, 1, 0, 1, 1, and 0, 1. And I signify these states with circles. And then to specify the state transitions or where I go from one state to another, which depends on both the current state that I'm in as well as the input, which I've just shown up here in the next state table. I can draw arrows to signify those transitions. So for example, looking at our next state table, when I'm in state 0, 0, depending on the input, if X is a 0, I stay in that state 0, 0. And if it's a 1, so I'm in state 0, 0, my input's a 1, then I go on to state 1, 0. Oops, over here in this column, the next state is 1, 0. In state 2, or 1, 0, if my input's a 0, again I stay in the same state, 1, 0. But if my input's a 1, then I go on to state 3. From state 3, if it's a 0, I stay in the state again. And if the input's a 1, then I see that I transition to state 1. And then from state 1, again, kind of starting to see a pattern here. If my input is a 0, I stay in state 1. And if it's a 1, then I transition to state 0. Now the outputs I can list on these edges as well since they depend on the state as well as the inputs for this particular sequential circuit. So I'll put a slash here and say that the output is actually always 0 unless I'm in state 1 and the input is 1. So for a 1, I transition from 0, 1 to 0 and my output's a 1. And all the other cases, my output is going to be 0. So to recap, my states are listed in the circles, and my edges signify the transitions with the inputs and outputs listed like this. Okay, so let's look at how we can model this now with a timing diagram. And let's assume that my initial state is 0, 0. Sometimes we can signify this with just an arrow signifying the initial state. So I start off in state 0, 0, and the first input when I get to the first clock edge, we'll say that these are positive edge triggered flip-flops. The first input is a 1, so I look at my state diagram, I see that when I'm in state 0 and the input's 1, I transition to state 2. And my output is 0, both these states. And then on the next clock edge, again my input's a 1. When I'm in state 2 and I have a 1, then I transition to state 3, 1, 1. On the next clock edge, I have a 0, so I'll stay in state 3. Then I'll read a 1, and so I transition to state 0, 1. And then I have a 0, so I stay in 1. But then in 1 now, I have reading a value of 1, and so I transition to state 0, but my output will finally go high. So my output up to this point is low. And actually, when I'm in state 0, 1, in this clock period, when my input is high, my output's going to be high. And then again, when I'm in 0, 1 and the input is high, my output's high. But then on the very next clock period, I go back to 0, 0, and my output goes low. Okay, so this is the timing diagram for the sequential circuit, but what does this mean? What is the sequential circuit doing? Well, this is a little bit trickier, but let's try to analyze what's going on here. So my input, I read it on the clock pulses, the sequence, 1, 1, 0, 1, 0, 1, 1. And the output was 0 until I had this transition on the 6th clock cycle. So if I wanted to define some meaning to these states, 0, 0 is obviously my start state, but it also represents when I've read in through the input 4 1s, 8 1s, etc. So I've gone around this loop of 4 states and read in either 4 1s, 8 1s, 12 1s, etc. 0 1, the state 0 1 represents when I've read in 3 1s, 1 1 1 1, or read in 7 1s or 11 1s, etc. 2 represents when I've read in just 1 or 5 1s or 9 1s, etc. And 3 represents when I've read in 1 1, 2 1s, or 6 1s, or 10 1s, etc. And the output Z is only 1 when I'm in state 0, 1, and I'm transitioning to state 0, so I've just completed one loop around all 4 of these states. So Z is really 1 when the number of 1s read thus far is 0 mod 4, or a power of 4. So this would be the meaning that we could infer for this particular sequential circuit. So to recap, combinational circuits have no memory, have only combinational elements, and the output is a function only of the current inputs. For sequential circuits, they do have memory or storage. They have combinational components and they have storage elements, such as latches or flip-flops. And the output is a function of current inputs and previous inputs, that is, the current inputs and state, where the state is the binary information stored at any given time. And then we talked about synchronous circuits, which are sequential circuits that have all their storage elements being clocked and have their states changing simultaneously at fixed intervals, or with a periodic signal, in other words, what we call a clock.